హాయ్ ఫ్రెండ్స్, వెల్కమ్ టు జిఎంకే ట్యూటోరియల్స్. ఇప్పటివరకు ఎవరైనా ఇంకా మన ఛానల్ సబ్స్క్రైబ్ చేసుకోకుండా ఉంటే సో ప్లీజ్ సబ్స్క్రైబ్ అవర్ ఛానల్. సో టుడే వీఆర్ గోయింగ్ టు ఫోకసింగ్ ఆన్ సప్లై వోల్టేజ్ స్కేలింగ్ కంటిన్యూషన్. సో దట్ ఈస్ నథింగ్ బట్ డివైస్ ఫ్యూచర్ సైజ్ స్కేలింగ్. ఓకే, సో లెట్ us see. So device future size scaling. Generally, nowadays the continuous improvement in the process technology and photolithographic techniques have made the fabrication of the mass transistors of a smaller and smaller dimensions to provide a higher packaging density. That means more number of components are inserted in the more number of components are placed in the corresponding intrinsic semiconductor, right? So that is generally called as a packaging density. Means that more number of components are embedded in a single semiconductor die compared to the previous generation, as well as a reduction in the future size reduces the gate capacitance. This leads to the improvement in the performance. Whenever we are going to designing the smaller and smaller dimensions of the mass transistors, obviously this capacitance leads to improve. Means the size of the gate capacitance is also decreases. That is adversely improves the performance of the device also. This is opened up for possibility of the scaling devices future size to compensate for the loss in the performance due to the voltage scaling. Generally, we know that voltage scaling plays a very important role. If you reduce the voltage scaling, obviously the total power dissipation is also decreases. But if you go for the device future size scaling, this is one of the possibility. The gate capacitance will be reduced. That leads to improves the performance of the corresponding circuit also, as well as the reduction of the size, the dimension of the MOSFET, generally called as a scaling. Right? So to characterize the process of scaling, a parameter generally just is known as a scaling parameter for representation point of view. There are generally two basic approaches for the device scaling. One is nothing but a constant field scaling. Second one is nothing but a constant voltage scaling. The name itself represents constant field scaling. That means in this consideration we have to maintain a constant field, and as well as in case of the constant voltage scaling we are maintaining the voltage is a common parameter, right? So first of all we have to discussing about the constant field scaling. Let us see very clearly. In constant field scaling, which is also known as a full scaling, constant field scaling is also known as a full scaling. The supply voltage is also scaled down to maintain the electric field as the previous generation technology. In case of the constant field scaling, we have to reduce the supply voltage, but we need to maintain the corresponding electric field within the device. That is very important. Let us see, these are some of the statistics that represents from 1985 to 2009, when the CMOS devices scale dimensions is obviously reduced to the very small dimension, right? In the first one 2.5 will be there in the 1985. 1987 it is 1.7. 1989 it is 1.2. If you go for 2007 0.065, but if you go for 2009 it is around 0.045. That means when the technology goes on increasing, the size of the device is also increases, right? So based on this one we have to think about how much small devices are fabricated nowadays because of your very advanced compared to the 2009. So obviously we can designing more and more smaller dimensions of the MOSFETs in the semiconductor applications, right? So coming to the next one, in case of the constant field scaling, if you scale down the corresponding metal oxide semiconductor field effect transistor, obviously some of the physical parameters is obviously decreases, right? So that is nothing but So TOX means TOX dash represents the new generation. That means before generation semiconductor dimension can be treated as a TOX, and scale down device dimensions can be treated as a TOX, right? So where S is nothing but a scaling parameter. With the help of a scaling parameter we will consider the remaining approaches. So let us see in this one by one. So TOX represents where TOX dash is nothing but a new generation. New generation. So TOX represents the old generation. That is a very important consideration. So based on that one we can represent this one. Where ND dash is nothing but in order to maintain the corresponding constant field in the corresponding device, this concentration is also increased by a factor S. As well as where L dash represents the new length generation, so that is equal to previous length generation is by a scaling factor S. As well as X represents the junction depth, that is also decreased by a factor of S. W dash is nothing but width, that is also decreased by a factor of S. And Na bar is equal to nothing but a concentration of the corresponding doping concentration, that is also increased by a factor of S. Okay, so this is a representation of the corresponding MOSFET. It is nothing but a substrate. Okay, this is nothing but a drain, this is nothing but a gate terminal, this is also source, right? Oxide layer. That means if the dimensions are decreases, obviously what happens is that the corresponding all the internal physical parameters are going to be decreases. As the physical parameters are going to be decreases, what are the electrical parameters affect? That is a very important consideration in this scenario. So let us see what is the situation of the corresponding electrical parameters. This table which gives a comparison of the previous one, quantity before scaling and after scaling. So let us see one by one. So first one is nothing but channel length, that is also decreased by a factor of let us see first one. Wait a minute, guys. So channel length, that is nothing but L. This channel length in after scaling is equal to L dash is equal to L by S, as well as channel width W, that is also W is equal to W dash by W by S. Gate oxide thickness is also decreased by a factor of S. Channel junction depth we can represent it as a XG. Power supply voltage VDD, that is also decreased by a factor of S. Threshold voltage VTO, that is also called as a threshold voltage with respect to the zero bias, that is also decreased by a factor of S. And Na and D values are increased by a factor of S because of we need to maintain a electric field within the device. Obviously we need to increase the doping concentrations, right? That is the most important points we have to consider here. So let us see as a consequence of the scaling, what are the various electrical parameters are affected due to the physical parameters, sizes and corresponding changes. Why? Because we are considering the electrical parameters means that these electrical parameters decides the performance of the device. So for that purpose, compulsory you need to consider these parameters within the device. Okay, so as a consequence, scaling various electrical parameters are affected. For example, the gate oxide capacitance for unit area is increased by a factor It is increased by a factor of s, and it is also given by cox dash is equal to epsilon ox into t dash of ox, that is equal to epsilon tox dash is equal to, that is generally called as a thickness of the oxide layer, that is also decreased by a factor s, right? So from that we can finally we know that the corresponding so S into Cox is equal to is increased by a factor of S, as well as coming to the length and width of the performance parameters also scale down by a factor of S. Therefore, W by L remains unchanged because of W by L is also S, and the length is also decreased by a factor of S. Therefore, the ratio of W by L is also maintains a unchanged. So, the transconductance parameter Kn is also scaled down by a factor S. So both the linear mode and saturation mode drain currents is also decreased by a factor of S, that is also represented in the form of a equation IDS dash is equal to linear, within the bracket linear represents, so that is a linear current in the corresponding equation, as well as Kn dash by 2 into VGS minus VT into VDS minus VDS whole square, VDS square. So where we these all represented with this some complement format or dash format, that is represents a new generation. Obviously gate to source voltage is also decreased, as well as threshold voltage is also decreased, and VDS voltage is also all the parameters are decreased, means the overall drain current is also decreased by a factor of S. That means in case of saturation as well as linear currents are decreased, right? So from that, as the both the supply voltage and the drain current are scaled down by a factor S, the power dissipation is also reduced by a factor of S square. This is a significant reduction in the power dissipation, is the most attractive feature of the constant field scaling approach. So for that purpose, in our low power applications, we first of all we have to prefer only constant field scaling, but it is also having some drawbacks will be there. Each and every methodology is also having some limitations, right? So that limitations, if you are controlling, obviously that is the best approach for any kind of the method. It may be VLSI, it may, if you go for any kind of the applications point of view. Another important parameter is the power density for unit area. So power density for unit area is also unchanged, because the area and power both dissipation both are reduced by a factor of S square, as the gate oxide capacitance is also reduced by a factor of Fs. There is a reduction in the both rise and fall times of the devices also. That means whenever the power density is also unchanged, means that is the advantage actually. If the power dissipation, power density is increases, means that at that time it creates a hot spot, right? So that is a problem actually, right? So coming to the next one, this shows the how the comparisons of the electrical parameter. So Cg is nothing but gate capacitance. It can be calculated as W dash L dash Cox. Obviously we know that C dash of Cox dash is equal to S into Cox. If you are substituting those two values, and W and L values also decreased by a parameter S, therefore overall value is also equal to Cg by S. Okay, therefore that leads to the corresponding Cg, that is nothing but gate capacitance is decreased by a factor of S. So that represents in the box itself also. The drain current ID is also decreased by a factor S. Power dissipation P is equal to P by S square, as well as power density unchanged. Delay time TD is also decreased by a factor, as well as energy is equal to P into TD. So from that, energy is also decreased by a factor of SS cube, right? These are the some of the advantages in case of the constant field scaling. Smaller device sizes leads to reducing the chip area, as well as higher yield, and more number of integrated circuits are for corresponding wafer, as well as coming to the higher speed of operation. Because of a smaller delay, it leads to improvement in the performance also. Third one is nothing but reduced power consumption because of smaller supply voltage and device currents. So with this our supply voltage scaling, how we are going to perform the supply voltage in this scenario, right? So జస్ట్ ఐ విల్ ఎక్స్ప్లెయిన్ వెరీ ఫ్యూ సెకండ్స్ ఇన్ తెలుగు. జస్ట్ ఐ విల్ వైండ్ అప్ ది సెషన్. సో కంప్లీట్గా ఈ డివైస్ ఫ్యూచర్ సైజ్ స్కేలింగ్ అంటే ఏంటంటే ప్రజెంట్ యూస్ చేస్తున్న ఈ టెక్నాలజీ వల్ల సో మెనీ అప్లికేషన్స్ కానీ సో మెనీ అడ్వాన్స్డ్ ఇన్ ద టెక్నాలజీని బేస్ చేసుకొని ఈ లో పవర్ చిప్స్ అనేవి చాలా స్మాలర్ డైమెన్షన్స్లో డిజైన్ చేయగలుగుతున్నాం. దానివల్ల ఏమవుతుందంటే చాలా కాంపోనెంట్స్ని ఒక చిన్న సెమీ కండక్టర్ చిప్లో ఎంబెడెడ్ చేయగలుగుతున్నాం కంపేర్ టు ది ప్రీవియస్ మోడల్తో కంపేర్ చేస్తే. దానివల్ల ఏమవుతుందంటే ఎప్పుడైతే మనం స్మాలర్ నెంబర్లో డివైస్ చేయగలుగుతున్నామో ఆబ్వియస్లీ ఏదైతే లాస్ ఉంటుందో సప్లై వోల్టేజ్ తగ్గించడం వల్ల దాన్ని మనం కంపెన్సేట్ చేయొచ్చు. ఎలా కంపెన్సేట్ చేస్తుందంటే ఎప్పుడైతే స్మాలర్ డైమెన్షన్స్కి రెడ్యూస్ చేసినామో గేట్ కెపాసిటెన్స్ వాల్యూ తగ్గిపోతుంది. గేట్ కెపాసిటెన్స్ ఎప్పుడైతే తగ్గిందో ఆబ్వియస్లీ పర్ఫార్మెన్స్ వాల్యూ అనేది కూడా ఇంప్రూవ్ చేయొచ్చు. సో ఇక్కడ స్కేలింగ్ అంటే ఒక డివైస్ యొక్క డైమెన్షన్ తగ్గిస్తే దాన్ని జనరల్లీ మనం స్కేలింగ్ అని చెప్తాం. దాన్ని మనం ఇక్కడ ఎస్ అనే వాల్యూతో రిప్రజెంట్ చేస్తాం. ఈ టూ అప్రోచెస్ అంటే మనం ఈ వోల్టేజ్ని ఎలా తగ్గించాలనేది టూ అప్రోచెస్ ఉన్నాయి. ఒకటి కాన్స్టెంట్ ఫీల్డ్ స్కేలింగ్ అండ్ కాన్స్టెంట్ వోల్టేజ్ స్కేలింగ్. ఈ కాన్స్టెంట్ ఫీల్డ్ స్కేలింగ్లో ఏం చేస్తాం అంటే సప్లై వోల్టేజ్ యాజ్ వెల్ యాజ్ థ్రెషోల్డ్ వోల్టేజ్ని కూడా రెండింటిని తగ్గిస్తాం విత్ ది హెల్ప్ ఆఫ్ రిమైనింగ్ పారామీటర్స్తో కలిపి. సో ఈ స్టాటిస్టిక్స్ ఏం చెప్తుందంటే ఎవ్రీ ఇయర్ అడ్వాన్స్మెంట్ వల్ల ఈ సైజ్ ఆఫ్ ది డివైజెస్ అనేది కూడా చాలా తక్కువ రేంజ్లో డిజైన్ చేయగలుగుతున్నాం. అప్రాక్సిమేట్లీ 0.045 ఇన్ 2009. సో కంపేర్ చేసుకుని ఇప్పుడు 2022లో ఉన్నాం కాబట్టి ఆబ్వియస్లీ ది సైజ్ ఆఫ్ ది డివైస్ ఇంకా స్మాలర్ డైమెన్షన్లో మనం డిజైన్ చేయగలము. ఓకేనా. సో దిస్ ఈజ్ రిప్రజెంట్స్ ది కాన్స్టెంట్ ఫీల్డ్ స్కేలింగ్ ఎలా ఉంటుంది, దాని ఫిజికల్ పారామీటర్స్ ఎలా చేంజ్ అవుతున్నాయి అని ఈ బాక్స్లో రిప్రజెంట్ చేస్తాం. లెంగ్త్ ఎలా చేంజ్ అయింది బై ఎస్, డబ్ల్యూ అనేది బై ఎస్, ఈ డాష్ ఆఫ్ ఎక్స్ ఎలా చేంజ్ అయింది. So ND and NA and ND is nothing but doping constant. These are two are increased by a factor s. ఎందుకంటే మనం ఇంటర్నల్గా సర్క్యూట్లో సమ్ కాన్స్టెంట్ ఫీల్డ్ మెయింటైన్ చేయాలి దానికోసం, రైట్. దీనివల్ల ఎలక్ట్రికల్ పారామీటర్స్ ఎలా వేరియేషన్స్ ఉంటాయి. సిఓఎక్స్లో చేంజెస్ వచ్చి ఎస్ ఇంటూ సిఓఎక్స్ అయింది. డ్రైన్ కరెంట్ కూడా డిక్రీజ్డ్ బై ఫ్యాక్టర్. సో డ్రైన్ కరెంట్ డిక్రీజ్ అయింది, సప్లై వోల్టేజ్ తగ్గిస్తున్నా అంటే ఓవరాల్గా పవర్ డెసిపేషన్ అనేది కూడా తగ్గిపోతుంది. సో పవర్ డెసిపేషన్ తగ్గటం అనేది మనకు చాలా ఇంపార్టెంట్ పారామీటర్ ఇక్కడ, రైట్. సో దీస్ ఆర్ ది సమ్ ఆఫ్ ది ఎలక్ట్రికల్ క్యారెక్టరిస్టిక్స్. సో అడ్వాంటేజెస్లో స్మాలర్ డివైజెస్ని డిజైన్ కలర్ ఎక్కువ కాంపోనెంట్స్ని చిన్న సర్క్యూట్లో డిజైన్ చేస్తున్నాం అని చెప్తున్నాం. సో ప్యాకేజ్ స్పీడ్ ఆఫ్ ది సిస్టమ్ కూడా చాలా ఫాస్ట్గా ఉంటుంది బికాస్ ఆఫ్ డిలే చాలా తక్కువగా ఉంటుంది కాబట్టి రెడ్యూస్డ్ పవర్ కన్జంప్షన్ బికాస్ ఆఫ్ ది స్మాలర్ సప్లై వోల్టేజ్ అండ్ డివైస్ కరెంట్స్. So with this I can wind up this session. Thank you for watching GMK tutorials. Thank you.